Good evening. Hello and welcome. I'm Tony Burton, Secretary of the Society. A couple of housekeeping things. Please turn down or turn off your mobile phones. There's no planned fire drills tonight, so if there are any fires and the fire alarms go off, please leave the building at the back and at the sides. And the way to the toilets is at the back and down the stairs. You can't get them this way, okay? So I'm sure, as a young boy, I was fascinated by the question, was there life out there on in the universe? I used to look out at the night sky and just wonder. And then I thought, it's going to be very difficult to know, because other than the nearby planets, how are we ever going to go anywhere to find out? But things have changed, and you remember our talk in January from David Rosario, who talked about the amazing James Webb Space Telescope. And he ended his talk by saying that many new discoveries were expected from that telescope, which was unique in its power and capacity. And you'll hear about one of those new developments tonight from Professor Madhusudhan from the University of Cambridge. The professor took his first degree in India and then a master's and a doctorate at MIT in America. And he then was attracted to the UK and has been at Cambridge for 11 years. He's a bit shy about saying it, but I think this is his first proper visit to Glasgow. So give him a good welcome.
Hello everyone, good evening. First of all, I would like to thank the Society for inviting me to be here and to share with you some of the breakthroughs that are happening at the cutting edge of astronomy. More specifically, I'll say at the outset that we are living in a truly profound time in modern science, not just modern astronomy, modern science. And the reason for that is precisely what Tony alluded to, is that it's not just you, Tony, who was asking that question. Humanity, our species, has been asking that question for a few thousands of years, right? Right from the very beginning, philosophers at the very beginning, a few thousand years ago, when science was being formalized in its very infancy, they were already asking that question across cultures, right? So it is something very fundamental about our species to be asking if we are alone in the universe or not. And there have been various attempts. People have tried in all sorts of ways, but never before had there been a realistic chance. We can always aspire to discover things, but there is also, you need to have a realistic chance of discovering things. So it has never been the case that there was a realistic chance of actually detecting signatures of life. We had to be lucky in the past. But things have changed just in the past couple of decades to an extent that today, if you ask anyone working in this field, exoplanet science that I work in, what are the odds of finding life? People are more likely to say, actually, it could happen in the next couple of decades. It could even happen in the next 10 years. It could happen in the next 5 years. And that is shocking, right? I don't think any of you would believe if I said there is a chance that we could discover life in the next 5 years. No, right? It just seems so unrealistic. But I will convince you by the end of the talk that that may actually happen. We don't know for sure, but to take away the basic point that we even have a chance of that happening is a big development in and of itself. And that chance only improves over like the next decade or two, and there are telescopes being planned that are specifically being designed to look for life. And I'll show you with JWST, we already have a chance of finding some biomarker elsewhere. It may take us much longer to establish a certain signature as coming from life, but we can already make the first inroads into that problem. So I hope you get the gravity of the situation just at the outset, that for thousands of years we have been trying, and for the first time in the history of our species, it may actually happen on a few decades time frame at max, if there is life out there, right? So I'll start with that sort of grand reality that we are facing. And my job today is to take you through what's happening in the field and to the very front of it. By the end of the talk, you will be sitting right at the very cutting edge of this field and know the answer to the question, how likely is it that we are going to detect life anytime soon? Okay, so you ready? Cool. First of all, I would like to thank a lot of my collaborators here who have contributed to various things that I'm going to show, various results. And of course, all of these results are happening with big telescopes like the James Webb Space Telescope, and thousands of people have worked over decades to make it happen. So it's kudos to all those people. It's really to our species that we are at this stage and these developments are happening. And I'm just here as to tell you the story of what's happening. Okay. So when you think about trying to find life elsewhere, or is there life elsewhere, the first question that comes to mind, or the first impression that comes to mind, is an Earth-like planet around a sun-like star. It's only very natural, right? We think of home, and if we are thinking about aliens, we say, well, there should be another planet like the Earth around a sun-like star, and maybe life like Earth, and we should look for it. So for decades, for basically a better part of the last century, whenever there have been attempts for realistic searches for life, that is the concept you start with usually. Okay? When we build telescopes or any sort of facility to look for life elsewhere, that is this starting point, and it's a reasonable starting point. But there are a few problems with that, technical problems, very, very, very practical problems. So today, if I say I want to detect life on an Earth twin, an exact Earth replica around another star, there are two problems with that. One is that we don't have an analog, an Earth analog elsewhere that we know of. Okay, so the quest stopped before it started. So we don't even know of an exact Earth-like planet elsewhere, so we can't look for one. The second problem is that even if we did, even if there was an Earth-like planet around a sun-like star we knew, we currently don't have the capability, the observational capability like the telescopes, to be able to detect an atmospheric signature around such a planet that can tell us that it's due to life. So those are two very practical problems. It's not philosophical, it's practical. There are two very practical problems for that. So how do we go about this problem? The one big thing that happened in the last 3 decades, how many people have heard of exoplanets? Many of us, right? Exoplanets, just for completeness, are planets around other stars, extrasolar planets, right? Planets beyond the solar system. The first exoplanets around sun-like stars were discovered just about 30 years ago. Okay? So until then, if you think about it, right, until 30 years ago, we knew of no planet outside the solar system, let alone thinking about life or atmospheric processes or so. We just didn't know of any planet outside the solar system, just about 30 years ago. And in 30 years, we have discovered thousands of these planets. So where we are right now, if you ask the statistics, how likely is it to find a star with a planet around it, it's 100% almost. That's profound, right? You go into the night sky, just walk into the night sky, point at a random star, chances are it's got a planet around it. It's not a guess. That's what our statistics are telling us. Like all these planets are discovered in the solar neighborhood, close by, astronomically. And our statistics say that almost every star should have a planet around it, at least one. And to go from not knowing any planet around another star to saying that almost every star should have a planet around it, that's a radical change already, right? All that happened in merely 3 decades. Yet for millennia, thousands of years, humanity has been asking that question: are there planets elsewhere? So if you think of all of these things as major breakthroughs which are just normalized very quickly, now it's obvious, of course there are planets everywhere. But that itself was a big breakthrough. And you'll see on this plot here is shown the size and orbital period on the x-axis. In the solar system, if you looked at the planets and their sizes, so there are 3 classes of planets. So there is Earth and all the terrestrial planets, Venus, Mars, and so on, which are Earth size or smaller. And then there are the ice giants, Neptune and Uranus, that are roughly 4 times Earth size. So the radius of Neptune is 4 times Earth radius. And then there is Jupiter and Saturn, roughly 10 to 11 times larger than Earth. So if you just took the solar system and asked what kind of planets are there, that's it. You got like 3 classes of planets: the terrestrial planets, the ice giants, and the gas giants. So for the past century, in modern science, modern planetary science, all our theories of planet formation, planetary structure, and so on, all of those were built around that quantization in sizes, that categorization of sizes. So we had like all our nice planet formation theories nicely fine-tuned to explain what we see in the solar system. Minor catch again. When we found exoplanets, there's thousands of exoplanets, and you just plot their radii as is being done here, just plot the radii and periods, orbital periods, you see that there is no quantization in nature, right? The solar system is not representative. Yet until 30 years ago, that's all we thought, that the solar system must be how planets exist out there. There is, you can see in this y-axis here, it's a continuum of radii. All kinds of planets are out there. So just from measuring the size of a planet and doing that for thousands of planets, there's a big open question here. How do these planets form? We don't even know they existed, right? So for example, these planets in between, between Earth and Neptune, there is no analog in the solar system, yet those are the most dominant planets out there. These are called sub-Neptunes, planets smaller than Neptune. Okay? We'll revisit that category again and again in this talk. But you'll see that those planets are the dominant planets in the exoplanet population. Yet there is no analog in the solar system, so we don't know what these planets are. Are these bigger versions of Earth, or are they smaller versions of Neptune? So there is a big debate in the field. Are these super Earths or mini Neptunes? So you can see that I just talked all this while I'm just talking about one observable, that is the radius, the size of the planet, and already there are fundamental questions in that. But we have gone ahead and measured lots of properties, their radii, their masses, their orbital parameters, and now we are talking about measuring their atmospheres. So there is vast diversity in all kinds of properties, everything that we are seeing right now, and that opens so many questions. And that deluge of science is what we are operating within right now. So just to give you the magnitude of the operations that are happening, all kinds of observations are happening, all kinds of theories are being framed. This is a field very much at the cusp of new science that's happening right there. And there are various facilities. These are all various telescopes. These are all space telescopes for planet detection. All of these telescopes, these 3 telescopes have discovered thousands of planets. All these data are just from one telescope, Kepler. And then there is one more telescope, Plato, coming later this decade in the next couple of years, which is going to look for Earth-like planets around Sun-like stars. You know, like when I first said we don't have an analog, turns out the goal of this facility is literally to look for those planets. So in terms of planet detection, it's not a big problem anymore, in the sense that we know lots of planets and we know that they're extremely diverse and extremely common. So where do we go from here? So remember, in my first slide, I said the problem of searching for life is that we don't have an Earth analog. And then in the next slide, I said, but there are thousands of other kinds of planets, just not an Earth analog. So then if you put 2 and 2 together, we can work out a solution probably. What do? We say, let's look at these planets that are in the sub-Neptune regime between Earth and Neptune. Okay? And let's ask the basic question. We have so far been fixated on Earth-like planets in the search for life, but is there a possibility that planets may be slightly bigger than Earth, slightly different from Earth? Maybe they could host life. Is it possible? Right? We can certainly ask that basic question. And if you crack that puzzle, if you have established that there are other kinds of planets, maybe bigger than Earth, that could host life, then we are golden. We have lots of such planets. You like that as a solution? So this talk will explore that in great detail. That is what's happening at the cutting edge right now. So we are harnessing the diversity of exoplanets that we are seeing and reframing our question as to how to search for life. Instead of being fixated on Earth-like planets, we are saying, let's go and look everywhere and see if we can find some. So you're beginning to see the story unravel. What are those things that will get us closer even before we find life on an Earth-like planet? So that is the new frontier in the search for life. We have terrestrial planets in the solar system, which have these nitrogen, oxygen, carbon dioxide-rich atmospheres. These are heavy atmospheres. On the other hand, end of the radius scale, we have the Neptune, in the sub-Neptune regime I'm speaking. We have Neptune, which is a hydrogen-rich atmosphere. This is molecular hydrogen, the lightest gas in the universe. Between those two extremes, there is no analog in the solar system, so we don't know what these sub-Neptunes are like. So we have to operate with a wide catchment area here. We have to try all kinds of internal structures, all kinds of atmospheric compositions, and just see what is out there. And maybe we'll find a way to connect the dots and find habitability or signatures of life elsewhere. Okay? So that's our goal here. Now, so I've talked about planet detection, but if you want to distinguish between these different kinds of objects, I've already given you the clue, right? So between these two planets, the main difference is the atmospheric composition, right? Which means if you want to establish anything about physical and chemical processes on other planets, the next step beyond just measuring their masses and radii, which we have done very well and are doing well, is to measure their atmospheres. Okay? So I'll give you one slide which will summarize a 24-lecture course I teach at Cambridge. So bear with me. This is the summary of all of atmospheric characterization, how you do atmospheric characterization of exoplanets. So basically, in one slide, on the top you'll see that these are light of various wavelengths, ultraviolet light, optical light, infrared light, and so on and so forth. Depending on which wavelength of light you observe these planets in, you probe a different layer in the atmosphere. So the infrared light penetrates deepest in the atmosphere, and then the optical and UV and so on. These are some technical terms. If you don't understand them, that's fine. This is just for completeness that I'm showing all this for those of you who are interested. The main point to take away is that in an atmosphere, like for example on Earth, as you rise up in the atmosphere, you're probing different processes, atmospheric processes at different levels in the atmosphere. Deepest in the atmosphere, most of the gases, this is for a giant planet, let's say with a very deep atmosphere, most of your chemicals tend to be in chemical equilibrium because the pressure and temperature is high enough that reactions happen very fast and they equilibrate very quickly. As you go higher and higher, the atmospheric processes try to disturb your chemical equilibrium. So winds, for example, is something that you can relate to, will move stuff around, so will disturb the chemical equilibrium. Clouds and hazes you are very familiar with here, right? So that's another process that can take, that can be in or out of equilibrium. Thermal inversion, so if you go higher up in the atmosphere, until a certain point the temperature decreases, but if you keep going up, the temperature actually starts increasing again. And that's happening because of the ozone layer, which intercepts the incoming UV radiation and re-radiates and does this temperature inversion at the top. So this is just to give you a sense of all the complex interplay between chemistry and physical processes that happen to give rise to all these properties that you see in an atmosphere. The point is, we can actually today probe all these processes in exoplanets. And I'm going to show you some examples of those. Okay? By looking at different wavelengths of like light at different wavelengths, we can probe different levels in these atmospheres and work out what these atmospheric processes are on an exoplanet, which could be hundreds of light years away. Okay? So we are going to look into how we do that, actually, technically. And also, depending on which wavelength of light you probe, you can measure different chemicals in the atmosphere. So you can measure molecules in the deep atmosphere where all the action is happening. But if you look in the UV, these molecules go up and get dissociated, and you can see these elements that constituted those molecules escaping into the outer space. So we can also detect those today. Why am I specifically mentioning this point? It's because if you want to detect a biosignature, you want to detect molecules that are given out by life, right? So you have the clue here that you want to look at this region of the atmosphere. Okay, so in the infrared/red optical wavelengths, where molecules have strong spectroscopic features. So then how do we do it? And the technicality of how we do it, I'll just give you a couple of slides. I'll have to see how to play this. So, my movie isn't playing. Okay, there we go. So this is a graphic of a transiting planet. So as you know, when the star is on its own, you will see just the starlight with your telescope. But when the planet comes in front of the star, you'll see a little dip in that starlight, right? So this is just plotting brightness of the star over time. So this dip basically is what tells you that a planet has gone in front of it. Okay, so this is like if you're an amateur astronomer and you're looking at transits of Venus in front of the sun, you would have seen something like this. Turns out most of what we are learning about this atmospheric characterization of exoplanets is coming using this technique. There are also other techniques, but most of what I'm going to talk about today is coming from this transit technique. So what's happening is that this dip in the light that you have seen here, this depth of the transit is proportional to the ratio of the projected area of the planet over the star. And that's just the radius ratio squared. Okay? But that ratio, this is called the transit depth, the delta, but that ratio is going to be different at different wavelengths of light if there is an atmosphere around it. Okay? Again, I'm getting a bit technical here, so please bear with me. This will help you appreciate the kind of things that we do. So let's say you didn't have any atmosphere, you just have a solid planet, a spherical ball going in front of the star, then it won't change, the transit depth won't change as a function of wavelength. But if you have an atmosphere around it which selectively absorbs light in some wavelengths than others, then your planet will appear bigger or smaller depending on whether there is absorption in the atmosphere. And that absorption will be caused by some molecule or some chemical species that's present in the atmosphere. So if you turn the problem around, by measuring the variation in that transit depth as a function of wavelength, we can work out what are the chemicals that are in the planet's atmosphere. So I'm giving you an example here for just in this wavelength range from 1.1 to 1.7 micron. This was obtained with the Hubble Space Telescope just about a decade ago. And you'll see that these points with error bars are data. This is just the red curve is just a model. But you'll see that in this region it's pretty flat because there is no absorption there. But then you see this jump. And that jump is happening because of water vapor in the atmosphere of the planet. Okay? And we know from laboratory experiments here on Earth that water vapor absorbs at these wavelengths. And that is how we can tell that if we are seeing that bump in that spectrum, that's water vapor. We do this in a bit more sophisticated manner than just pointing at it, but you get the idea. Right? So we have spectral templates of various molecules on Earth. And then when we look at these spectroscopic observations like this, we do this template matching effectively and work out what are the chemicals in the planet's atmosphere that are causing these undulations with wavelength of the transit depth. So this, in a very simple example, is a transmission spectrum and how you extract chemical information from it. So this is transit spectroscopy for you. And today, with the James Webb Space Telescope, the phenomenal revolution that's happening is that this was the best we could do with the Hubble Space Telescope just over a decade ago. So you can see that the wavelength range is like maximum up to 1.6, 1.7 micron, right? But today, we can get all the way up to, this spectrum is showing you up to 5 micron, but we can keep going up to 20 microns. So all of a sudden, instead of, we were only able to measure water vapor actually with the Hubble Space Telescope in giant planets, in these big hot giant planets. But with JWST, we are able to measure lots of molecules, and this one spectrum shows you several of those molecules. This is literally the first spectrum that was obtained, one of the first spectra that was obtained with JWST, and right off the bat we could detect carbon dioxide, sulfur dioxide, carbon monoxide, hydrogen sulfide, all these molecules, many of them for the first time ever. And that is cool, right? What I haven't told you, the little secret, if you look at those error bars, can you guess how big that error bar is? Like it's about 10 parts per million. Change in light of the star at 10 parts per order, 10 parts per million as a function of wavelength is what you're seeing right there, or a few 10 parts per million of that order. And that's what JWST gives you. And with that sort of phenomenal precision and wavelength range, we are opening a wide range of processes to examination right now in exoplanets. Okay? Remember, these planets are hundreds of light years away. Okay? So I'm going to show you many more of these, so stay with me. And that was just my introduction. So now you know all the basics you need to know to take you right to the very cutting edge of the field. So far we have looked at giant planets, we have looked at phenomenal spectra, we saw how we can detect molecules, we saw how we can detect spectroscopic features in general, you know how the method works, you know how atmospheric observations work, all of that. And we are going to apply all those concepts to the question we are going to ask today. How do we detect life? Right? So I'm going to introduce you several concepts now, focused exclusively on that question. So I'm going to introduce you to the concept of exoplanet habitability, and then I'll introduce you to this Hycean paradigm, and then we talk about biosignatures, and then we'll look at case study with real observations. You ready? Let's go. So exoplanet habitability, those are all the factors that affect whether a planet can be habitable. That's intended to overwhelm you, so don't be surprised. So this is just to convey the simple message that it's not easy to establish whether a planet out there is habitable. We are not going there, right? This is like, as I said, hundreds of light years away, maybe tens of light years away. So it's not a simple concept to just understand whether for example, a lot of times you'll hear about whether there is liquid water on the surface is what determines planetary habitability. It's not quite that simple. Okay? There are lots of factors. The star plays a huge role in all of this. The star can be very active and can destroy the atmosphere, can destroy the oceans, and so on. The age of the star makes a difference. The internal structure and what sort of volcanic history the planet has affects habitability. How the atmospheric processes operate, how much escape is happening from the atmosphere makes a difference. The temperature structure of the atmosphere makes a difference, whether you can have liquid water or not. The planetary system, what other objects are there in the system also make a difference, right? You could have large impacts and decimate life, for example, or not. So a lot of these factors affect habitability. Then how do we make progress? Well, we have to start somewhere. Classically, the place to start is by saying, okay, we understand there are all these factors that can affect habitability, but let's start simple. Let's say there is an exact Earth-like planet around a given star. What is the distance from the star the planet can be and still host liquid water if the atmosphere is exactly like Earth, if it's an Earth analog? And that is where this concept of a habitable zone comes in. The definition is this band here is basically the distance. If you have any star, this is a sun-like star, but if you go to smaller stars, the star gets cooler as well. So the habitable zone is basically what is the distance from the star your planet can be and still host liquid water on the surface if the atmosphere is Earth-like. So naturally, if the star is smaller and cooler, you can be closer to the star to receive the same amount of radiation. So your habitable zone, entirety of it will be closer in. So this is a convenient definition, operating definition in the field, and people have been working on that basis. So when we talk about habitable planets, this is what we are talking about, habitable zone planets, planets that are in the habitable zone, but that doesn't guarantee habitability for all the reasons I mentioned in the previous slide. Okay? So this is the habitable zone, and then there are several exoplanets that have been discovered which are in the habitable zones of their host stars. Now this may sound a little bit contradictory to what I said at the beginning, that we don't have an Earth analog. But it's not a contradiction, because these habitable planets I'm going to talk about are planets that are around smaller stars. M dwarfs is what we call them. So yes, they're in the habitable zone of an M dwarf, but not around a sun-like star. Okay? So this is an example. TRAPPIST-1c is a famous example where there are 4 planets in the habitable zone of a very small star. The star is only a 1/10 of the mass of the sun. Okay? So, and it's very cold. It's a 1/3 of the temperature and so on. So it's very cold. So you can see that entire planetary system fits in this little small region, even within the orbit of Mercury. Okay? But these systems are good because the star is so small, the planets can be so close, so your transits are more frequent, so you can see them more often. Okay? So there are all these benefits of looking at planets around M dwarfs. However, if you ask this question, if you take all the planets that we have so far and ask how many of them are in the habitable zone, how many of them have temperatures that are like Earth, maybe the stars are not sun-like, but how many of planets are there that are Earth-like? So here I'm just showing you a plot of radius versus period. You have seen say, a similar plot before, but here I'm showing you equilibrium temperature. It's an average temperature taking into account the stellar radiation. If you do that exercise and say I want 300 Kelvin roughly, which is similar to what you have on Earth, and then I want Earth-sized planets, and I put a box around it, that's how many planets we have today. Okay? Order 5, certainly less than 10 transiting planets that are Earth-sized, even around M dwarfs. And that's difficult if you want to search for life, and 4 of those are in the same system that I showed you in the last slide. Right? So there is a dearth of rocky planets, Earth-like rocky planets around, even around M dwarfs. So in order to search for life, we ask this big picture question that I posed at the very beginning of the talk. We are going to ask, well, clearly we are having a hard time finding Earth-like planets around any kind of star, certainly habitable planets. So we got to broaden our definitions and ask the basic question, what are the limits on planet mass, radius, temperature that are conducive for habitability? Can planets be bigger and slightly hotter maybe and still be habitable? Right? So that is the question we are going to ask. So that's where this Hycean paradigm comes in. So this journey started in the middle of just before COVID, actually, in late 2019, early 2020, is this planet K218b was being observed with the Hubble Space Telescope. Now, let's go through the properties of this planet. This is a planet that's about 2.5 times Earth size. Okay? The radius is 2.6, as you can see on the slide there. The planet is quite big. It's 9 Earth masses. Okay, 8.6 times the Earth mass. The only thing that's going in favor of this planet in terms of habitability is its equilibrium temperature. You see that the equilibrium temperature there is below 300 Kelvin. So at least we have one thing going for us, right? So temperature, we're saying that the average temperature is just right, but then the planet is too big. No one, when the planet was discovered, no one would have thought that this would have anything to do with habitability. What happens is that when you have a big planet, the pressure from its atmosphere becomes so high that it can crush any life. And as the pressure increases, your temperature will also increase. Yes, the average temperature in the upper atmosphere may be 200 or 250, 300 Kelvin, but as you go deeper, the temperature also increases. So all those factors mean that you can't have life. This is why we think Neptune, for example, can't have life. It's just too big. But how big is too big? We didn't know. So anything bigger than Earth or slightly like maybe Earth and a half, people were thinking that those can't be habitable. But then what we did is, I think, like that was the turning point for us, is that we said, well, why don't we just think about it a bit more? Just build models and see if there is any chance that this planet could be habitable. Okay? So we did that. So at that time, I showed you this nice HST spectrum of a giant planet, right, with this water feature. This was also measured with HST, except with about 9 transits. For the hot Jupiter giant planet, I showed you 1 transit. This is 9 transits stacked together to get this little spectrum blip of a starlight. So it's a very, very expensive spectrum obtained with Hubble. And we only got, this was obtained by 2 different teams. This particular data is shown from this paper here. And we went ahead and extracted the atmospheric properties, and we agreed with other studies at the time that that could be due to H2O, but there was also debate, maybe it's due to methane. The reason for that is that H2 and methane have features at the same wavelengths, around 1.4 micron. Okay, so it's very hard to disentangle them when you have just one blip of a feature like this. But what we could say for sure is that it is a hydrogen-rich atmosphere, and whether it's water vapor or methane, those gases are in small quantities, but the majority of the composition is hydrogen. So then we went one step further. I'm walking you through the process of science here, like how actually things work behind the scenes. We said, let's take that boundary condition that there's a hydrogen envelope and build planets in our computer models of different compositions, interior compositions, and see if we can explain the bulk parameters, the mass and radius of the planet. Okay, so that was a mouthful. So if you didn't get, I'm going to dig a little bit deeper in here in that concept. So this is what is known as a mass radius plot. So mass on the x-axis, radius on the y-axis. These curves are showing constant composition curves. In other words, if you have a pure iron sphere, this curve will tell you for a given mass what could be its radius. Okay? This blue curve here will tell you if you have a pure water sphere and of a given mass, what could be its radius. And in simple terms, what this is showing is that the radius and mass of the planet sits slightly above the pure water curve, okay, at room temperature, which means it needs a hydrogen-rich atmosphere, which is the next lighter element, lighter than water. And that matches the observations that we actually found the atmosphere is hydrogen-rich. So that's good. So what we did is we came up with these 3 scenarios, in all of which could explain the bulk parameters and atmosphere of the planet. The planet could be a water world, enormous amounts of water in the planet, and a thin hydrogen atmosphere. It could be a mini Neptune, like how our Neptune is, some amount of an atmosphere, some amount of water in the interior, and a rocky core as well. Or it could be a rocky world, a large super Earth with a thick hydrogen atmosphere. All of these compositions can explain the bulk properties of the planet. Okay? So it's what is known as a degenerate problem, in the sense that many different solutions can explain your data. But what was the interesting thing in all of this is that because of this coupled atmosphere interior modeling, we could work out the range of solutions at the surface between the atmosphere and the interior. So what are the temperature pressure conditions at the boundary between the atmosphere and interior is what we were calculating. And those are these red curves. Okay? These are loci for different parameters. And you will see, again, long story short, you will see that some of those solutions lies in the liquid part of the water phase diagram. Okay? I'll summarize all of this by saying that most of the solutions needed to explain the mass and radius of the planet said that the surface would be too hot for life. You can't have life, it can't be habitable. However, there is a small fraction of those solutions that I just pointed at which do allow for a liquid water surface. Okay? So science, this is again another tale in science where it's not that you have an idea, you go and you find it. Usually you find a number of solutions, and within those solutions you find pockets of solutions that are interesting. So in this case, we saw a small number of solutions that say that, okay, you could actually have liquid water on the surface of this planet if the atmosphere is thin enough. And then we said, well, let's look further then, explore that even further. And then what we did is that we went beyond this particular planet, K218b, and said, if K218b can have a small set of solutions that allow for liquid water, what is the entire space of planets out there, the parameters of planets out there that could also have such solutions that allow for liquid water? And that is what this concept of Hycean worlds is. Okay? Hycean worlds, the word Hycean, as some of you may know, is a portmanteau of hydrogen and ocean. Right? So hydrogen, ocean, Hycean. Right? So what we found is that there is actually a large region in this mass radius plane that allows for such solutions. So we call this the Hycean mass radius plane, and there are a number of planets now that also fit that category that hadn't been explored before. If we ask the same question, well, what does that do to the habitable zone? Because we saw the terrestrial habitable zone was this. Does it do anything to the habitable zone if we assume the planet is not Earth-like, it's a Hycean? Turns out, it expands it enormously. So now you see the terrestrial habitable zone, that's the Hycean habitable zone. So suddenly, we went from knowing just a small number of habitable planets that are, that we can observe, to saying actually now there's a much larger area in orbital separations, masses, and radii that can allow for habitable conditions. We don't know if they're actually habitable, but in principle they do allow for those solutions. Okay? So there is a wide-ranging debate, as you would expect, as to where the boundaries actually lie, because for all these models you have to make some assumptions when you build these models. But where do these boundaries lie? How close can the planet be and still be habitable? In other words, what is the inner habitable zone for the boundary for the Hycean worlds? All of these things are being debated right now. But the point is, if you have these Hycean worlds, hydrogen atmospheres and ocean worlds underneath, that increases the space of planets, the number of planets that you can look for biosignatures. Okay? So that was 2021. Just in the this paper was written entirely in the middle of COVID. So we already had identified a dozen planets, and then there was this new regime in planetary habitability that opened up, and turns out that was the same year that JWST was launched. Okay, so it was primed for JWST. So what I'm going to tell you in the remaining few minutes of this talk is the story of how the observations came around in whether, and you'll see whether or not they match the theory. You still with me? Okay. I know I'm going through a lot of technical detail here, but I hope that is helping you appreciate the depths of the science that is happening. So let's now look at biosignatures, right? So if you have these Hycean worlds, what are their biosignatures? Turns out, if you look at an Earth-like planet, just take the Earth's experience and say, what are the prominent biomarkers in the Earth's atmosphere? We have the usual molecules that we can think of. Oxygen and its derivative ozone are very good biomarkers on Earth. Only life produces it on Earth. Methane is a very good biomarker. There are some geological sources that also produce a small amount of methane, but by and large, it's from life. Nitrous oxide is another molecule that's predominantly, almost entirely from life. And ammonia, again, mostly from life, but also has some sources. Those are primary biomarkers, significant biomarkers. And then there are a number of secondary biomarkers, dimethyl sulfide, methyl chloride, and so on, which are produced in very small quantities. We are talking about few parts per billion in abundance, in volume mixing ratios in the atmosphere. but that are produced uniquely by life. Those don't have any other geological processes. So those are called secondary biomarkers, less in abundance, but strong in relation to life. So those are for Earth-like planets. But when you look at these Hycean worlds, the atmospheres are hydrogen rich, which means some of the molecules that we expect from life, like methane or ammonia and so on, could in principle be made just from atmospheric processes in a hydrogen rich atmosphere. Okay, so even if life could produce them, they wouldn't be definitive indicators of life. On the other hand, several of these secondary biomarkers would be more promising biomarkers in a Hycean atmosphere. Okay, so that's the sort of difference between looking at an Earth-like planet or a Hycean planet. The biosignatures vary. But then you have to ask, what is the detectability? Where do you expect these features? So in the very beginning, again, in my one slide intro to exoplanet atmospheres, I said how you want to look in the infrared to look at molecular features. This is showing you those features. Remember how I said for water vapor, there is a spectral feature at 1.4 micron? These are showing all the spectral features of various molecules in the infrared, okay? Just these features. And these are the templates that we have from laboratory experiments on Earth. So if you're looking at a biomarker, an atmospheric signature of a habitable planet, we'll be template matching that signature with all these signatures that I'm showing you right now. And that's how you extract whether any of these molecules are in there, okay? So I've showed you what JWST can do for giant planets. Now, if you look at Earth-like planets, we talked about TRAPPIST-1 planets. The summary is that you need hundreds of hours of JWST time to detect a biomarker. So even for TRAPPIST-1 planets, the few planets that we have, and people are trying. We haven't found any so far. It's difficult. And this is an example showing how difficult it is. This is one spectrum of a TRAPPIST-1 planet, and it's being pretty flat. But what we are also learning is that the stellar contamination is a bigger problem. Because when you go to the smaller stars, the stars also become very active. That's, again, a bit of a technical detail. But lots of flares from the stars disrupt your atmospheric observations. So it's difficult to look at these rocky planets around late M doors. But if you look at these Hycean candidates, then what we found, this was already predicted, we predicted it before JWST flew, is that you can actually detect these molecules that I was just talking about, dimethyl sulfide, methyl chloride, and so on, in few tens of hours of JWST time. So not only is that we have opened the parameter space of planetary properties for habitability, but they're also easier for atmospheric observations. Okay? So with that theoretical backdrop, we decided to go and look at K218b. So now we are getting into the crux of the matter of where we are at the cutting edge right now. So just before JWST flew, we put in these proposals to look at the atmosphere of K218b, and not to look for biosignatures or anything, just to see what molecules are there, if at all. And we were selected, and we got time, about 20 hours with JWST. 3 transits for those who are technically inclined. This is all the information of the observations. We got time to look at 3 transits, and in this particular work that I'm going to talk about, we have reduced observations for 2 transits. And summary is that between these 2 transits, we span the 1 to 5 micron range. So this is with an instrument called NIRISS-SOS. This is NIRSPEC G395H. Between these 2, we have roughly 1 to 5 micron wavelength range. And the 2 observations together is about 14 hours of JWST time. Okay? So I want to show you what JWST can do with just 14 hours. Okay? So again, this is a transit I showed you in the movie. This is for your amusement. I'm showing what a transit looks like of K218b with JWST. And this is for those who are looking at telescopes and detectors. This is what the spectrum looks like on a detector. Okay? You can ask me questions, technical questions about that later. This is with, so now let's look at the actual spectrum. So we saw this with Hubble Space Telescope. This is with about 60 hours of Hubble time. Let's look at what 14 hours of JWST will give you, right? One feature, 1 to 1.7 micron, and that's what you get with JWST. Okay? All the points with error bars are actual data, and you see the wavelength range is 1 to 5 micron, and you see these multiple features. There are 5 features of methane in here. Let me break it to you that this is the first time humanity has ever discovered carbon-based molecules in a habitable zone exoplanet. When you just see a spectrum, when you see a spectrum like that, it may not mean very much, but this is one of the most profound observations that have been made, in my view, in exoplanet science so far. Because we had never measured methane in an exoplanet, in a small exoplanet before, ever. And we had been looking for like a decade with Hubble and so on, and we never knew. One observation with JWST, and you get these, with 2 instruments, you get these 5 features, definitive methane detections. And we detected another molecule, CO2, which we didn't expect, carbon dioxide. Okay? What do these observations tell us? Remember how I was telling you we use template match? I'm showing you the templates in the background here. These are theoretical models with various templates, so you can see these are methane features, and those are in this model that reflect the data. Yeah? So this is how we do the template matching. We make these models, and then we recursively match them with the data and find out. Same with CO2. You see this big CO2 bump in the template. You see that in the data as well. Okay? So there's no question that these molecules are there, at least methane and carbon dioxide. That's phenomenal. Again, I said template matching all the time, but the formal phrasing of that is atmospheric retrieval. Again, for the technically inclined, this is the data. You have your data, you have your parametric model, and you do a rigorous Bayesian parameter estimation, and out come the estimates of the parameters, which are these molecules, temperature parameters, and so on and so forth. Again, we can go into details if you're interested. This is actually what we extract from the data, the posterior distributions of the various molecules. So you can see, those who are interested in statistics will know that this is a clear detection of methane with very small error bars. We are detecting methane at about half a dex precision, which is a factor of 3 or so. Okay? And at 1% abundance in the atmosphere. Just imagine this. This planet is 120 light years away. We are saying we can detect the abundance of methane in its atmosphere and say that it's at 1% with precision of 0.5 dex. And we're not even seeing the planet, remember, we're just seeing a blip in the starlight. That's phenomenal, right? All of this is crazy to me, even if I'm a practitioner in the field. I'm constantly mystified by how we're able to pull this off. And same with carbon dioxide. But we also don't see several species we had expected before if this were a deep atmosphere, like water vapor, ammonia, and so on and so forth. Dimethyl sulfide, we are seeing a tentative evidence for. You may have seen a lot of news about this molecule. This is a biomarker on Earth. We're not sure if the molecule is there, but we are seeing these tentative peaks which go away if we massage the data enough, but we are not sure if that's the right thing to do. Whatever. Our approach has been to be the devil's advocate and put in as many free parameters as possible to make the signal go away, okay? And not claim if that happens. You can't do that for methane and CO2. Whatever we do to the data, they survive. Dimethyl sulfide, not so much. So we are not claiming that as a robust signature, but we see it at some level, and there is more data is coming, so we'll know one way or the other. But even just the detection of the first 2 carbon-bearing molecules, the non-detections of several of these molecules are already telling us something profound. What are they telling us? Remember these 3 scenarios I mentioned about? A deep atmosphere that has a rocky core inside or a Neptune-like interior versus a Hycean world with a thin atmosphere. Turns out each of those scenarios has a specific chemical fingerprint. Again, it'll take a chemistry class to explain it, but I'll try in a very short session here. If you have a deep atmosphere, in the very beginning I said that if you go very deep, the pressure is high enough that all your molecules will be in chemical equilibrium, right? You remember that? Turns out, if you have an atmosphere this cold and you have normal abundances of carbon oxygen and so on, in chemical equilibrium, you expect a lot of methane and ammonia. So if you have a deep atmosphere, those molecules will be circulated in the atmosphere, and you expect to see a lot of methane, ammonia, and carbon monoxide in the upper atmosphere. The way you won't see it is if you have a shallow atmosphere which cuts off that recycling. So your pressure is no longer high enough to maintain chemical equilibrium, so you kill off some of these molecules, like ammonia is the first thing that gets killed. And especially if you have a water layer, it absorbs ammonia very quickly. Ammonia is very soluble. Okay? So these predictions were made before the JWST observations, that if you don't see ammonia and you see CO2 and methane, that would be an indicator of a Hycean world. And turns out that is what we are seeing. So how often does it happen that you make a theoretical prediction before the observations and the observations go and confirm those? It's phenomenal. We shouldn't be complacent about it. We should still explore other avenues, obviously, but that's what happened. So this is basically what has opened an entirely new era in studying habitable zone planets. Because for once we know that there is a chance, there is proof, there is a theory, there was a prediction, there was an observation that confirmed the theoretical prediction and has opened a field that is full of debates right now on various aspects. Which of these planets can be habitable? What other chemistries can potentially explain these observations, and so on and so forth. So I'm going to wrap up with the future outlook in a few slides here. Obviously, like any big breakthrough, in any cutting edge field, you have to have lots of open questions when your first data comes. That's just the norm. And obviously, there are many open questions, as I just pointed out. Is the liquid ocean surface actually possible? Is the albedo, the reflection in the atmosphere, enough to maintain the temperatures low enough to give you this liquid ocean in the surface? What is the temperature structure of the atmosphere? What are all the processes that affect that temperature structure? Is a deep atmosphere still possible, and somehow you explain ammonia by another process that we don't know of? We ought to be skeptical. We ought to be looking for all these other explanations. Now, I will say there have been a lot of debates on these topics. I'm just citing the latest works here, which are basically, and I'm involved in this, where we looked at each of these hypotheses, and we are in a kind of a difficult spot right now because I have to say currently the only way we can explain all these observations together, even just the presence of CH4, the methane and CO2, and non-detection of ammonia and carbon monoxide, the only way we are being able to explain right now is if you have an ocean. Okay, maybe Hyceans are real. We don't know. But currently, so far, that's where we are. We need more theoretical development. We want to keep looking for other hypotheses, obviously, but this is where it stands. That being said, even if there is let's say there is an ocean, there are other questions. What are the robust indicators of life on Hycean worlds? Okay, is life actually possible? Because our concepts of how life formed needs an Earth-like planet, because that's what we are used to thinking. But if you have just ocean and no land, how do you actually form life to begin with, right? And what would be a robust biosignature? What would be life like on such planets? These are all open questions. And it's happening right now. Like, people are looking into these things right now. And finally, how common are these things? Did we just get lucky with K218b? Is it just a one-time thing, or do we have more examples like that? And what observation constraints are possible? So how many people think we got lucky? Is that a full hand or a half hand? Sorry. So,
not sure.
Oh, not okay. Good. Okay, not sure. How many people think we got lucky? Okay, we have a few. We have a few. Okay, so I'll have the answer for you immediately. So we have several more observations coming, but I will just touch upon a few of these questions. Is life possible on Hycean worlds? So we looked at these things. To begin with, we said, what would a Hycean world look like? What would the ocean look like? Because we don't have a concept of a planet, well, we don't have an example here, of a planet where there is just ocean and no land. Well, how deep can the ocean go? On Earth, for reference, several of you may know, the deepest oceans on Earth would be order 10 kilometers. Okay? But if you made like models of these Hycean worlds, you'll see that the oceans can extend up to 100 kilometers or even more, hundreds of kilometers. Well, what happens at that depth? Where do you stop? where is the ocean floor? Turns out there can be so much water that you actually won't see a sea bed in the usual sense. This water at depth converts into high pressure ice. So your ocean floor is ice at high pressure. And then you have to drill through the ice for many, many, many more hundreds of kilometers to actually hit rock. Okay? So these are the concepts of such planets where we don't have any intuition from what we see on Earth, but that's what we have to contend with. Okay? So we are doing a lot of these theoretical models right now to understand these things. And then to answer this question of is life actually possible, we tried to ask a more simple question. Are all the bioessential elements that are essential for life on Earth, like the carbon, nitrogen, phosphorus, and so on, would those still be available if you have just an ocean world? And in this study, we found, to our surprise, that actually that is not a limitation, because when you have this external delivery through these impact meteorites and comets and so on, they can deliver enough of these elements into the Hycean ocean to match the levels that we see in the Earth's oceans. Not just now, but in the Archean Earth, in the primordial Earth's oceans. Okay? So availability of bioessential elements is not the problem. But still, how do you actually make life? Well, that's a tough question because we don't even know how life originated on Earth. So I think we should excuse ourselves a little bit for not knowing the answer to that just yet. So I'll answer the last question here. Is K218b unique? Turns out, earlier this year, we looked at, several teams looked at another planet, and that's the spectrum.
Thank you. Thank you for that. Okay, so what an amazing story. I mean, it wasn't that long ago when we didn't know there were things like exoplanets, so we could only imagine. Now we have all this discovery. Now, the professor will be happy to take questions. We've got some possible questions online. And we've got two people with microphones. And so put your hands up, and we'll take questions from all over the hall. At the back, right at the back on the left.
Fragments of information using JWST. How are you calibrating the Earth's orbit around the Sun to give the equivalent of someone looking in? You can obviously do it from close by. I'm wondering if there are any proposals for some of the stellar explorers that are moving out towards the end of the solar system to turn around and try and look back and measure these elements of Earth as it goes around the Sun.
Yeah, so I went a bit fast through that, but there was a slide on, I actually should show this. So when I was talking about biomarkers, I showed a spectrum of Earth looked from space. And we can actually see some of those features that. So this is sort of an Earth-shine spectrum seen from a reflected light from the moon, actually, where you can see some of the features in the Earth spectrum, the carbon dioxide, methane, and so on and so forth. And there have also been spectra of the Earth taken from satellites, as you were saying, like probes going outward, and we can yeah, we can see the Earth spectrum pretty clearly like that and sort of make out the spectral features. And that's basically the principle of Earth remote sensing, right? So satellites looking back at Earth in infrared and other wavelengths to make out the Earth's atmospheric features. So we're using basically similar techniques, but modulated for exoplanetary conditions.
Is it possible to judge the age of the different planets?
So age estimation directly we won't be able to measure. The way you can get a rough constraint on the age is by looking at the stellar age. And that also has some challenges in measuring ages of, especially most of these planets are around M dwarfs, which make it a bit more difficult to measure the stellar ages as well. There are technical difficulties there. But that's the best we can do, is to look at the stellar age and then try to get an estimate of the planet age from that.
I think it's really beautiful seeing the data from the Hubble telescope, that it's such a small snapshot and being able to take so much information from that. And then obviously going forward and how that is opened out with the increased modernization of the instrumentation, where do you feel the future is as far as how we look at the universe, where like the next telescopes, how will they improve what we see?
I'll show you a slide on that. I did put a few more futuristic slides in case there were, sorry, how do I operate? Let me show you. So the big picture to take away from all of this is that, sorry. I mean, the bottom line here is that we made 3 fundamental advancements, right? I mean, we made like the first sort of observations of potentially habitable planets. We don't know. So the first contact, so to speak, of habitability. And then there is the unique congruence of theory and observation, which is precious for astrophysics. And then we found this new class of planets. Now, to answer your question, this sets the stage for what we are going to do in the future, right? This is saying that we have like a set of objects now. We have ordered a dozen planets that we can look at with JWST. And we also have the theoretical framework and how to interpret them, and there will obviously be more debate and so on the theoretical side, but we at least have a framework. And then if we get lucky and if we do establish that these are indeed habitable planets, this is where the optimism comes that the observations are already happening, right? In the next 5 years, there will be many more of those, and we could get lucky and find a biomarker. Right? So that is, to me, where the future is. So currently we are doing it with JWST, but there is also the extremely large telescope coming on ground. That's a 40-meter class telescope. That's the largest ever built on ground. And within those, we'll be making more of these detections. So if I may just wrap this up with one final thing. In my mind, actually, the question is not whether we will detect life, but it's more like whether we are prepared to find life as we don't know it. In other words, we may detect a biomarker, but we may find it very hard to establish that that is uniquely because of life. And that's where I think the future is heading. I don't doubt that we will detect some of these molecules with more observations.
Thank you. I was curious about a lot of the biomarkers. Thank you. A lot of the biomarkers seem to have carbon related to it. What is it about carbon that's so versatile? Are there other versatile, chemical elements that could substitute for carbon, or are we looking for carbon because that's what we're
Yeah. So I mean, so life on Earth is mostly carbon-based, right? So that's why we are seeing a lot of carbon, and carbon forms very good covalent bonds very easily. So you get a lot of carbon in organic compounds by definition. The other element, which you'll see in some of the most robust biomarkers, actually carbon not just from biomarkers, right? Even geological molecules like carbon dioxide and methane also can be produced geologically and so on, have carbon in them. But if you say, look at molecules that are specifically coming from life very robustly, they also have sulfur in them oftentimes. So that's another element. So all these dimethyl sulfide and so on, some of these molecules have sulfur that binds with carbon as well. So there was a question here actually, did we?
Yes, my question's in the same line as the last question, really. Life on our planet has evolved with a particular chemical form. Is it possible that we have life on other planets that we don't know about that has evolved in a completely different chemical way, which may have different markers altogether?
It is very much possible. I mean, how we go about it, we wouldn't know. That's the difficulty. I mean, people do some calculations and so on, but we are so early in the process that most of the time, as you can tell from my talk, we are going roughly from where we are right now, like, the kind of life that we know of, the kind of templates, because you need to have a template, at least, to interpret what you're looking, right? And those templates are Earth-based. So we are sort of limited in that sense. But I'm sure I know that people are also looking at what other kinds of biochemistries may be possible, what other molecules could be produced and so on. And that's what I mean by this question here, right? All we can do observationally, very practically, is measure a spectrum and interpret it as molecules. And to extract those molecules, you need to have the templates, which are by definition molecules we know of on Earth. That much we can do technically. But then what those molecules mean is an entirely different question, right? It's an infinite possibilities, which is basically what your question is about. We can try our best, and people are trying, but I can't point to a specific form of life that is different from what we know of on Earth. Sorry, I'm not sure if that answered your question, but that's the inherent difficulty of the problem. Thanks.
The other thing that life needs is time in the habitable zone. And yet, during the evolution of the solar system, planets were known to have moved in and out in terms of distance, and maybe Earth was just lucky. But with these candidate planets, is it possible to estimate the stability of their orbits and the stability of their stars?
Yeah, no, that's a very good question. When I was mentioning about habitability, and I said factors affecting habitability, that's one of the things I was also talking about, how stellar evolution can play a big role, like what stage the star is in can also affect your habitable zone. And as you said, these planets move back and forth, between the habitable zone and outside of it. For Hycean worlds, those calculations only very preliminary calculations have been done in that regard, but we are still very early stages of that. The way I look at it is the reverse, which is the minimum question we can ask is if the planet is in the habitable zone today. Right? Because there are objects that we are seeing today, and the first order question to ask is that is today a certain planet in the habitable zone? Can we look at its atmosphere and can we extract signals of life? And that's where we are right now. And we have about a dozen planets that we can look at with JWST. And then as the theoretical interpretations evolve, then the deeper level questions of, well, what is its formation history? Those sorts of questions will be asked next over time.
Hello? Oh, goodness. Thank you very much. That was hugely interesting, as much as it was bamboozling. Just a fundamental question. Are you looking to see if they are out there or whether there's a there that we can go to.
Okay, you have to read.
Yes. Are you looking to see if they are out there or whether we can go there?
Okay.
Or is it irrelevant?
No, the second question, the second one is irrelevant. Whether we can go there is basically irrelevant, and we can't go there. We know that for sure. But the first question is hugely relevant. And that's because there is a deep philosophical summary to everything that we are doing. Most of the time, one can lead oneself into thinking that the reason we are finding life is because we want to go there, or we want to find life like us, any forms of life that we see on Earth and so on. But my personal goal is actually a lot simpler, but also ends up being a lot more profound, which is we know physical processes, right? Almost every macroscopic physical process that we see on Earth, we have established that cosmically, like millions of light years away, they also work, many of the fundamental laws of physics. Same with chemistry. A lot of the chemical processes that we know on Earth also work cosmically. What we don't know is the universality of biology. So any indication of any biological process elsewhere completes the picture. And that to me is a very big deal, right? For our species to know that life is a process and it's a universal process. So that is what I think will have much, much wider ramifications than just finding, of course it's the same sort of philosophy, but of course at the end of the day we want to find life like Earth, but even like finding any kind of life means that we have breached that barrier. And once you've found one, it demonstrates the universality of it, and the options are endless after that.
Thank you very much.
When you identify life, as we know it or don't know it, what is the next practical step? What do you do next?
No, good question. I do have an answer to that, actually. So there are two answers, right? One is from a purely scientific process. Like if I treat life as any astronomical process that I'm out there looking, what do? You find one process, gravitational waves, let's say. You find one instance of it, you look for more. Right? You try to understand populations. You try to build a story about the universality of this process, how this process depends on various environmental factors. You look at different planets over different ages. You try to build a story, a philosophy, a full picture of how life operates in the universe. So you have one detection, but from that, you want to know much more than just that detection. So that's one very pragmatic way of operating. But then you can also think of how can you replicate conditions on Earth and understand processes here at home, right? So if you're seeing something in a hydrogen-rich atmosphere, a Hycean world, let's say, life is operating, you're only seeing a biosignature, but you can never actually say what kind of life it is, right? No matter how much of this theory development we do, it will always be lacking in the fine detail of what exact life is that. And the way around that is to try to replicate the conditions here on Earth and see how life behaves under those conditions, and if we can learn something fundamental about biology that way. Does that help, maybe?
Right. Are there any questions online?
Is the Hycean world that you've modelled, is that using liquid water, or have you considered other liquids, and do you think other liquids could support life without the presence of water?
So in the solar system, people have been thinking about those questions, other liquids. So for example, Titan has hydrocarbon lakes and a very rich organic chemistry. So that has motivated a lot of astrobiologists to think about, can liquid hydrocarbons host life? People do experiments in acids to see if life can survive, because turns out the atmosphere of Venus, you may have heard about phosphine and so on, which led to speculations that maybe there was at some point life on Venus. Then the question is, can life actually survive in acids, sulfuric acid? So people are doing that, but as far as the Hycean is concerned, we're only talking about liquid water oceans, because that is the easiest kind of planet to make from a formation point of view. Cosmically, hydrogen and water are literally the two most abundant materials in plant formation environments. Right? So you start simple, and you can make a Hycean pretty easily from those. So that's where we are. Do we have questions from students? Oh, there's one at the end.
Thank you so much. That was a really exciting talk. So you've mentioned some of the limitations. So I was just wondering, like, how far can we actually detect the blips? Like, is there like a distance that, at which point the data that we get is just not reliable, it's too noisy?
Yeah. Very good practical question. So K218b is about 120 light years away, so about 40 parsecs. There we can go slightly beyond that, but not much more. Then the data gets too noisy. So the spirit here is that you want your star around which the planet is orbiting to be as close as possible, so the signal to noise is very high. So most of our targets, we have about, as I said, like a dozen Hycean planets candidates identified. All of them are closer, most of them are closer than 100 light years. That's the rough order. You could go to maybe 200, but you're stretching it at that point.
Right, I think it's time to call a halt to the questions. I'd now like to hand over to our president, Professor Pat Monahan, to say a few words about this being a special lecture.
Thank you very much. Tony, can you hear me okay? Well, we've been on quite a journey, I think, into the world of astrochemistry, and it's a complex world. And I say that as somebody who failed her first chemistry exam at university and thereafter did no chemistry whatsoever. But the whole field is mind-blowing. And I think we're seeing the advances here as they're taking place. The enthusiasm is so infectious. Maybe if I was starting my career again, I might take more interest in chemistry, or pure chemistry anyway. I certainly was interested in biochemistry. But this kind of looking out into deep space and finding molecules there that tell you about the atmosphere is really astonishing. And we've heard in our previous talk about the James Webb Telescope and the leaps forward that telescope is enabling, not just in telling us about the structure of the universe, but telling us about whether we are alone within it is truly amazing. And also these Hycean worlds. I know we all sometimes feel like in Scotland we live in a water world, but it's nothing like what we've heard about. Now, I was at a meeting recently on the biodiversity crisis that we are facing in our own world. And one of the speakers said, we're getting to the point, because the search for life elsewhere is going nowhere, and it looks like we are alone in the universe, and we're getting to a point where humanity is holding in its hand not just the future of life on our planet, but the future of life in the whole universe. Well, it's reassuring to think that maybe that's not the case, and that if we blow it on this planet, which we look possibly that we may do it and we may blow life away completely, then it's maybe out there and life will continue, but maybe not. So there's a lot to think about in these kinds of issues. So before I go on to say why this is a special lecture, for the non-scientists amongst you, I'd just like to remind you that we're moving away from science in the next 2 lectures into a much more complicated and distressing world of politics to a degree, but more of that later. Now, why is this a special lecture? Well, we haven't really told the speaker this, but this is really our Thomas Graham lecture. And I'm going to present the Thomas Graham Medal. Now, Thomas Graham was a professor in Andersonian College here in the university. He was vice president of this society in 1834. Those of you who are interested in chemistry will know about Graham's law, and that it tells us a lot about the movement of gases, and also that's very relevant to atmospheric chemistry. So I'm going to present Madhu with the Society's Thomas Graham Medal, and, of course, the Society paperweight, which has astrology at its heart.
Thank you very much. That's such a pleasant surprise. Thank you. I really appreciate it. Yes, absolutely.
So there are drinks outside, and you can think more about watery worlds, and you can look forward to Jonathan Sumption's talk in 2 weeks' time. Thank you.